So our topics today is about magnetism. Okay. So let's look at the learning outcomes. So what you are going to learn today. So magnet, just like electric charges. So a magnet also has magnetic field. So how does magnetic field looks like? Okay. And the difference between ferromagnets and electromagnets. Ferromagnets is actually permanent magnet. Or I call it as born to be magnet, meaning that it is originally a magnet when it was first being invented or created. So ferromagnets. Electromagnets is temporary magnet. So the difference between them, what are they? So to determine the directions of magnetic field using right-hand grip rule, and also the relationship between the magnetic field and also current. Okay. So there are three types of orientation to determine the directions of magnetic field. So the first one is red wire, second one circular loop, and third one solenoid. So these are the three types of orientation. Okay. So since magnetic field is also a vector, that's why when coming to vector, we need to know the directions and also magnitude, right? So you have to find the resultant. Okay. So when we have magnetic field, likewise for electric force, for electrostatics, we will also have magnetic force. So how do we find the magnetic force? By using Fleming's left-hand rules. Okay. So magnetic force, there will also be resultant magnetic force. Okay. So, and also when we have two conductors, so what will be the resultant magnetic force as well? Okay, so meaning that in this topic we will learn about the characteristics of a magnet, okay, magnetic field and magnetic force. Okay. So what is actually magnet? Okay, magnet is a material or object that produces magnetic field. Okay, so when people ask you what is magnet, then we will usually say that something that can attract metal, right? But in the technical forms of explanation, so if you want to explain it in a more physics way, we say something that produces magnetic field. Okay, so it's the magnetic field that causes the magnet to be able to attract the metal. Okay, so what are the characteristics? The first one, all magnets have two poles or two ends, north pole and south pole. Okay, the first one. And the second one, just like electrostatics, like poles repel, unlike poles attract. Okay, so meaning that north pole will be repel against north pole, south pole repels against south pole, whereas north and south is attractive to each other. Okay, so another special characteristics of magnet, unlike electric charges, we can have separate or individual positive or negative charge existed individually. But for magnet, the north pole and south pole must be together. Meaning that, let's say if I have a magnet here and I cut them into half, what will happen? Okay, we will get a portion of this and another portion with this. Even though north pole is here, but the moment when you break them into half, what will happen is the ends that with existing north pole will be north pole, whereas on the other end will automatically be a south pole. Okay? So that is another special characteristics of magnet, meaning that your north pole and south pole must exist together on one magnet. Okay, so this is something that happened around us. We know that the Earth is a huge magnet, right? So can you tell me which A or B? Which one is actually the correct magnetic field? So I would like you to join this. And you choose the answer. You think first, according to the knowledge that you have regarding Earth magnetic field, and you choose whether 1 or 2, A or B, to be the correct Earth magnetic field. Okay, so what is your answer? So most of you choose 2. Any other answer? Any other answer? Also 2. 2, ah? Okay. So most of you choose 2, huh? Okay, so you choose 2 because you know that magnetic field moving from North Pole to South Pole, am I right? Okay, but I would like to tell you the correct answer is actually A. A? Huh, why? Okay, so there are 2 types of pole. One is geographically North Pole. So this is actually geographically North Pole. Okay. However, and this is geographically South Pole. Geographic means location, right? Okay. So, but actually inside the Earth, there is a huge magnet with here as South Pole, meaning that the geographically South Pole, is actually magnetic North Pole, and geographically North Pole is actually magnetic South Pole. So that's why when we place a compass anywhere here, the compass will always follow the direction of magnetic field. Magnetic field going up from magnetic north pole to magnetic south pole. Alright, so that's why when we place our compass will always point to geographically north pole. So that's why whenever you use compass, the directions where the compass shows, we call it, oh, that is where the north is. But in fact, inside the Earth itself, our geographically north pole is actually magnetic south pole. So that's why, if you know Chinese, Chinese people call compass as 指南针. 指南针 means the needle that points towards the south. So at first when we didn't know about this, we will find like, Chinese so stupid one, how come it's actually pointing towards north, but how come they say it's pointing towards the south? But actually for Chinese, they are referring to this magnetic south pole. So that's why compass is called as needle pointing toward the south. So that's why when next time when people ask you, how come Chinese, you're so stupid one, you call this as needles that points towards the south? Then you can explain to them, actually in terms of physics, okay, magnetic field point up from north, from magnetic north pole to magnetic south pole. Am I right? So if you say B is correct, meaning that this is north and this is south, meaning that geographically north pole is magnetically north pole. Geographically south pole is magnetic south pole. So your actual direction will be moving from north to south, am I right? So when you show your compass will actually point toward the south, won't be pointing to the north. Okay, so that's why Chinese, they're actually very smart. Why? Because they actually talks about physics, okay? So this one is just an extra information for you to know. The correct answer for the directions of magnetic field of the Earth is actually coming out from geographically south pole, going into geographically north pole. Why? Because inside the Earth itself, the pole for the magnet is the other way around. Okay? So you can read the further reading here by your own, Okay, so the difference between ferromagnets and electromagnets. So ferromagnets is a permanent magnet. So is that actually a born to be magnet? When it is first invented or when it is first born, it is already a magnet. Okay, so the one that you buy from Daiso, that is ferromagnet. So it's actually hard to magnetize, okay? Because it has to, this one we say, it has to be originally a magnet, difficult to trend. Okay, so it stays magnetized longer than temporary magnet. So the example, nickel, cobalt, nickel, aluminium. So they are actually original magnet. As for electromagnet, it is temporary magnet. So it can be magnetized. So how do you magnetize a metal into a magnet? You just put it together with a magnet for a very long time. Then the metal will, so when you separate them, then the metal will also be able to attract certain metal also. I mean, like, the strength is very weak, but it still can act as a magnet. So it's easy to magnetize, and at the same time, it lost the magnetism quickly also. So how do you, let's say if your scissor is being magnetized, so how would you want it to lose its magnetism? Just by dropping it on the floor, okay? Then you can lose the magnetism. And another way to build electromagnets is by building a coil, then allow the current to pass through. Okay, so this one will also magnetize the wire into a magnet. Okay, so let's say now we have a magnet here and we put the compass around the magnet. So this is what you will get, right? You will get the directions of compass. It seems like coming out from North Pole and going into South Pole. Okay, so if we connect the compass together, and this is our magnetic field, coming out from north and going into the south. And when we connect them as a closed loop, so inside the magnet itself, we will have our directions from south going to north. So this is the complete loop of magnetic field. Huh? No sound.
So do I go out? Because I did the test this morning and negative.
Oh, then we open the door.
She just like, this person.
I am now, according to after we will test the positive, right? So for the period of, like, let's say half a year, we are safe from COVID, like we won't get it again and we won't be contagious. Yeah? If me, that's okay. Okay. So another way of illustrating magnetic field is by using iron filling. Okay, so if you have done this in your primary school before or your high school, so you know, right? So when you pour the iron filling around a magnet, and you will also see the pattern of magnetic field. So actually it is a circle. So it's actually a closed loop types of circle. Okay, so the rules of thumb for magnetic field, the characteristics of magnetic field. Okay, so the directions of magnetic field is tangent to the field lines at any point in space, right? So what does it mean? So when we talk about magnetic field, it's actually a closed loop, right? So let's say now, what if I want to quantify a certain point on the magnetic field? So how do you know what is the direction? So to quantify a point on a circle, it is actually equivalent to the tangent, right? So what is actually tangent? Tangent means it is perpendicular to the radius of the circle. Okay, so let's say if now the directions of the magnetic field is going anti-clockwise. So at this point, what is the direction of magnetic field? The tangent, so it will be going up like this. Okay, so this is the tangent. The second one, the strength of the field is proportional to the closeness of the line. Okay, so meaning that if you look at here, the closer is the lines of magnetic field, the higher is the strength. Likewise, if compared to here, the distance between the lines is further away. So relatively, the strength of magnetic field at this point will be lower. The third one, magnetic field can never close. Okay, so they are actually, so if you look at here, the line, they never intersects. They are separated. So they never intersect, never close. Okay? Then magnetic field lines are continuous, forming a closed loop. Okay, so it's a closed loop, circle or oval. Okay. So now let's look at the first orientation. Magnetic field of a straight wire. So long straight wire like this. So how do we determine the directions of magnetic field? So by using right hand grip rule. Right hand grip rule, there are two properties here. Okay, with your thumb shows the directions of current, and the finger shows the directions of magnetic field. Okay, so let's say now, based on our diagram, the current going upwards. So we have current going upwards, so direction of thumb point upwards. So where does your finger shows? This is anti-clockwise from the top view, am I right? Okay, so this is how we determine the directions of magnetic field. Okay, then the magnitude, the values, the magnitude of this magnetic field of straight wire is given by this, mu naught I over 2 pi r. Mu naught is a constant permeability of free space, 4 pi times 10 to the power of -7. I will be the current over 2 pi r. R here is actually, let's say now I would like to determine what is the magnetic field at this point, point X. So X, R will be actually the distance between your point X and your wire. So this will be your R. So if you look at the diagram, R actually is equivalent to the radius of that circle, am I right? Okay, so R is actually the radius of the circle. Okay, but to be specific, it is the distance between your point X, and your wire. Okay, so remember our rules number 1. The directions of magnetic field at a point is tangent to the circle. So let's say now this is the directions of magnetic field. Right hand grip rule, going anti-clockwise from the top view. So what is the direction at point X only? Is equivalent to the tangent. Tangent, remember, must be perpendicular to the radius. Yeah? Okay, so this will be the magnetic field at point X. The directions of magnetic field at point X. Okay? So now, I would like you to, these are the pre-lecture exercises. So if you have gone through the videos, so there are some exercises for you to try. So I would like you to check your answer on there. Okay, so I will only do one question, let's say question 2 and 3. Okay, so how do you determine the directions? Since current is going downwards, so your thumb point downwards, the directions of magnetic field will be like this. So when we draw on this paper, yeah, let's say on this computer screen, so the screen here only shows about 2 dimensions, right? So how do you draw? Okay, if you want to draw as if it is 3 dimensions, so we know that it's going into here, coming out from here. Okay, but if you want to draw them in 2 dimensions only, so this is, you have to imagine it in 3D, am I right? But what if you only can draw in 2D? So we will have these 2 symbols to help you. Cross product and dot product. Cross product means going into the screen. Dot product means coming out from the screen. Okay, so let's say if you want to draw on here, what is the 2D types of drawing? So on the left-hand side, magnetic field is going into the screen, am I right? So what you can do is cross product on the left-hand side. On the right-hand side, magnetic field is coming out from the screen. So here will be dot product. Okay, so these are another way of drawing. Okay, so usually, in order for us to easier to write down the answer or to be specific, we will choose to use the dot and cross product to represent the 3D. Okay, so how do you memorize whether dot product and cross product, which one is into the page, which one is coming out from the page. So you just imagine when it is coming out from the page, your thumb is pointing out towards you. So what do you see on the tip of your thumb? It's like a dot, right? So dot means coming out from the screen. So when you turn the other way around, going into the screen, what do you see from this side of your hand? A lot of wrinkles, right? So these wrinkles are cross product. Wrinkles. The cross product means going into the screen. Okay. So now in our question 3, the current itself is a cross product. Cross means going into the screen. So how do you draw your magnetic field lines? Thumb pointing into the screen. Directions of finger is clockwise. Very good, So clockwise. Okay. So now this one, what if you are asked to determine the direction at a point only? So at this point, how would you draw the directions of magnetic field at point O? So I will do question 1 with you. 2, 3, 4, I want you to try. Okay, so question 1, your current going upwards, so magnetic field is coming out from the left-hand side, going into the right-hand side. So the magnetic field at point O is actually a dot product, right? Okay, so let's complete 2, 3, 4 and submit. Just draw the magnetic field at point O only. Don't draw the whole thing, but draw the magnetic field at point O. You can go to your browser, classpoint.apps, and the class code is 73567. Oh, wait, I think time is... Okay, again, Only two are joining. What happened to the rest? You all went back to sleep, is it? I know the weather is very good. Huh? The rest all went back to sleep. So, wake up. I think they went back to sleep already. What? Wi-Fi cannot what? Why that? Unable to join. Yo. Can you screenshot to me what happened? The class point, is it? What does it say? I go and troubleshoot. Oh, okay. Okay. Set. Okay, so now let's look at okay. Want to insert a slide. Okay, so now let's look at here. Yeah? Okay, so the first one is dot product. Second one, according to your right hand grip rule, current going downwards. So on the right hand side it is dot product, cross product. Very good. How about now here, question 3. This is your point. So what is actually the direction at point O? At point O only. So from your right hand grip rule, yes, it is going clockwise like this, right? So when passing through point O, this is your circle. Correct? So remember just now our rule of thumb number 1, it says that at a point it must be equivalent to the tangent. So you have to draw the tangent. So the tangent, it is, okay, this is your R. Your tangent must be perpendicular to R. Okay, so the direction, since now at this point it is going downwards, so this will be the directions of magnetic field, B. Okay, so question 4 also the same. Perpendicular to R, so draw your R, perpendicular to R. So according to right hand grip rule, coming out from the screen, so it is this. So this will be your magnetic field. Okay, at a point, when it says magnetic field, if it asks you to draw a circle, then yes, you draw a circle. But if it is at a specific point, make sure only one line. Okay. So it's the same also in this case. Okay. So this one has to be like this. This will be your magnetic field, and it is perpendicular to your R. Same here. This will be your magnetic field, perpendicular to R. Okay? Now let's look at the exercises. So this is a sample of questions whereby you have to determine both direction and also the magnitude. Okay, so wire at the coordinate of 0, 3. So here is 5 ampere. Direction, what is the directions and magnitude of the magnetic field at point X, which is 4, 0. So magnetic field, remember, it is a vector. So if it's a vector, you have to determine both directions and magnitude. So let's start from direction first. So it is a point. Start by drawing your R first. So the line would be the tangent line. Now what is the directions from your right hand grip rule? When passing through point X is going downwards. So this is your directions of magnetic field. So what is the values? So since this is a straight wire, okay, so use the formula for straight wire, mu naught 2I 2 pi r. So mu naught constant 4 pi times 10 to the power of negative 7. Current 5. R is the distance. So here 3 meter, from here to here is 4 meter. So the distance can be found from Pythagoras theorem. So it's actually 5 meters. So 2 pi 5. So answer is 2 times 10 to the power of negative 7 Tesla. Okay? Yeah. Now, next orientation is a circular loop. So circular loop, like you wrap or you coil the wire. How to determine what screen clear? Directions of tangent. Direction of tangent. Tangent, by using right hand grip rule, you know how to draw the tangent line, right? It is perpendicular to the radius. Direction, so once you have draw the tangent line, you draw the line first. Make sure it is perpendicular to the radius. Then directions whether up or down, use your right hand grip rule. Okay, current going into at the 5A, current going into this 5A. So when it passes through, can you see the screen? Can you see the screen? Cannot, huh? Can on Webex? Cannot. Oh, too bright, huh? How that? Okay. So what I want you to see here, okay, here, right? So you put your finger at the point where the current is. So this is where the current going in, am I right? So thumb, you stick it on this current going in. So point X is at here. So when your finger pass through point X, where is the direction? Where is the direction? Actually going down, right? So that's why it is going downwards. Okay, so that's why I said this topic is a topic whereby last time when they are having closed book examination. Okay, so this is the topic whereby you can cheat with your hands. And you will know that your hands are actually your best friend. Okay? So Sam, now move on to circular loop. So circular loop is when you coil your wire make them into circle. Okay, so for circular loop, the magnetic field at the center here means here. They are uniform. And they can be found by this formula, N mu naught I over 2R. N refers to the number of turns of your loop, mu naught the constant, I current over 2R, and this R is the radius of the loop. this radius of this circular loop. Okay, so it is uniform, meaning that at this point it is B. At center here, the value is also the same. Okay, the values of the magnetic field at the center of the circular coil is the same, uniform. Okay, so how do we determine the directions? Likewise, you can use your right hand grip rule. So just follow your finger to the directions of, like you follow the whole wire. So let's imagine this wire. So what we do is, our circular coil, your thumb, follow all the way. How does the coil go? So what can you see? At the center region of your coil, your magnetic field is going up like this, right? Huh? Okay. So you can determine also with right hand grip rule. Oh yeah? So this is actually in your pre-lecture videos. Okay? So using your right hand grip rule to determine the directions. Let's look at number 2. So following use your thumb, stick on this coil. So what you get at the center region, the directions is always going towards you. Am I right? Huh? So on the top view itself, it is going downwards at the center region. Huh? Okay? So let's try this exercise. Circular coil. So given number of turn is 10, magnetic field 2 times 10 to the power of negative 4 Tesla. Okay, unit for magnetic field is Tesla, SI unit. So determine the directions and find the radius given. Current is 5 ampere. So since this is a circular coil, so use the formula for circular coil. Okay, so magnetic field given 2 times 10 to the power of negative 4. Number of turn is 10. Mu naught current is unknown. The current is given 5. Radius is unknown. Okay, so solve this equation. Radius 0.157 meter. Find the directions of the magnetic field at the center of the coil. So center of the coil, the current going like this, right? So stick your thumb with the directions of current moving all the way together. So you will discover no matter where does it go, the directions of magnetic field at the center is always going into the screen. Okay? So instead of using thumb as current, we can actually interchange. Oh, got question, huh? So I don't know why. How, why so difficult? Here, you stick your thumb with the directions of the current. So, moving along the current. So what do you get? At this center here, you will discover your directions of finger, no matter where does it go, right, at any point. Your directions of finger is going into the screen. Okay? Or another way, like just now I haven't finished. Our thumb is the directions of current, finger is directions of magnetic field, right? So you can actually interchange. Let's say if now current is, if we use finger as current, so thumb will be the directions of magnetic field. So in this case, current move in clockwise direction. So clockwise using finger, map the clockwise direction. So where does the thumb show? Going into the screen. So this is the direction actually pointing towards the center of the coil only. Okay? Okay, huh? So in this case, you can use both current, magnetic field, or thumb is the magnetic field, but remember this one is showing the magnetic field at the center of the coil, whereby your finger shows the directions of current. Okay, next, another type of orientation is a solenoid. So solenoid, for solenoid also using right hand grip rule. So to make our life easier, the directions of finger shows the directions of current, whereby thumb shows the directions of magnetic field. Okay, so just imagine like you are holding the solenoid with your finger, follow the directions of the current, just like what the diagram is showing. Like you are holding according, and your finger follows the directions of current of the solenoid. So where does the thumb show? Pointing toward the left. Okay, so this one also refers to the magnetic field at the center of the solenoid also, which is here, the region that's shaded with yellow color. Alright? Okay, so the formula or the magnitude to find the magnitude of solenoid is given by this B equals to mu naught N over Li. So the difference here is this L. L refers to the length of solenoid. Length of solenoid is here. So it is not the length of the wire itself, but it's when it has been coiled into the solenoid. So what is the length? Okay? So looking for the directions. So usually how do we determine the directions? If let's say question 2, this is the question given saying that the current coming in from here. So going up, down. So usually for us to easier see the directions, I will draw the directions on the side which is nearer to us. So it is going downwards. So now imagine as if I am holding this solenoid. I'm holding this solenoid, right? So grabbing this solenoid, so it is like this. On the side that is far away from you, current up, going up, right? But the one that is facing towards you is down. So this is like when I'm grabbing the solenoid according to the directions of current, where does the thumb show? Shows to the right. So meaning that magnetic field coming out from here and going into here. Okay, so when we have magnetic field moving like this, isn't it this solenoid just look like a bar magnet? So solenoid can also turn into a bar magnet with the side whereby magnetic field coming out is the north pole, and the side whereby magnetic field going into will be the south pole. Okay? Yeah? So let's move on to the question. Length of the solenoid 10 cm, number of turns 400. carries current of 2 ampere. Find the field at the center. So magnetic field of solenoid, mu naught Ni divided by L. Mu naught constant, number of turn 400, current 2, length convert to SI unit 0.1. So answer is 0.01. SI unit Tesla. Okay, so something for you to think again. What is the difference between circular coil and solenoid? Just now both of them is being turned or is being wrapped into circle, but what is the difference? So let's say if you want to do a project and you coil your wire, then how do you know which formula should you use? Use the circular coil or solenoid? How will you differentiate the difference? Just simply use. How will you know like whether to use circular coil or solenoid? Anyone? Coil is just a wire. So but like how do you tell? Because both of them you have to coil them. It's a circle, like both of them have number of turns. So they are both coiled into a circle form. So how will you This is circular coil and this is solenoid. So how do you tell the difference? Solenoid is long wire, while circular coil is radius. Okay, something like this. So if you look at the formula itself, okay, formula for circular coil, divide by 2R. The formula for solenoid, divide by length. Okay, so meaning that solenoid is very, very long. That's why the length of the solenoid is very significant as compared to the radius of the coil. Okay? So that's why we can ignore the radius in our calculation. So if you look at the calculation, there is no radius. Even though solenoid, there is radius for solenoid. But because comparing the effect, the length of the solenoid is too significant or too large as compared to the radius, so that's why it can be ignored. Okay? Likewise, for circular coil, the radius is too big as compared to the length of the coil. So that's why we ignore the length in our calculation for circular coil. So in other words, we can say that solenoid is tall and thin, your circular coil is fat and short. Okay, so next time if you are working on your project, for example, so how do you know which formula to use? Compare between the radius and length. If your radius is very big as compared to the length, then that is a circular coil. So if your length is very big as compared to your radius, then that is a solenoid. Okay, so that is the difference between solenoid and circular coil. Okay. So since it is a vector, then when you draw the directions are positive or negative. So when it is vector, we know that positive or negative depends on the direction. So just like how you do for your vector questions, you have to assign a direction as positive and the other way around will be negative. So how do you determine the directions? By right hand grip rule. Okay, so this is how we determine the directions. So remember I said when we want to determine the magnetic field at a point, it must be a line. Even though we know that from our right hand grip rule it is a circle, but at the point it must be a line. So for example, at this point A, magnetic field generated by wire 1 at point A, according to right hand grip rule, it is going upwards. Why is it going upwards? Because this is the tangent perpendicular to the radius. Okay, so going upwards from right hand grip rule. Likewise, magnetic field generated at point A by wire 2 is also going upwards. So in this case, we assume going up as positive. So B1 plus B2, that is our resultant magnetic field. So second case, if now it is at point P. Don't understand why it is point up. Here, wire 1. So now you have to determine the magnetic field at point A. So when we say it is at a point, it must be tangent, right? So tangent, draw the tangent line perpendicular to your radius. So why is it going upwards from your right hand grip rule? Again, okay, now this is your wire 1 at here, am I right? Wire 1 into the screen. So point A is to the left of your wire 1, which is here. Correct? So using your right hand grip rule, going into the screen. So when it passes through point A, where does it go? The direction is just going up. So that's why magnetic field generated by wire 1 at point A is going upwards. Huh? Okay? So same goes for your B2, which is the magnetic field generated by wire 2 at point A. Again, now wire 2 is somewhere. Okay, wire 2 is somewhere here now. Your point A is still here. Okay, so using your right hand grip rule, going into the screen. So when it passes through point A, going up. So another line, which is B2 here. Now this is a vector. So assuming going upwards as positive, so B1 plus B2. Okay? So now what if, instead of point A, you are asked to determine the resultant at point P, at the center. So we have our two wires here. Can see? No. How? Okay. How about the whiteboard? Huh? Cannot. 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 Oh, just now was better.
That was clear.
Oh, okay, then we use this one. Okay, so these are the two wires and point P is here. Huh? So, wire 1 and wire 2. So where is B1? Also, your thumb point towards, stick on this wire, going to here. So when pass through point P is going downwards. So this is B1, right? Okay, once you have done with B1, find B2. B2 also comes, stick on this wire too. So when it turn around, reaching point P is just going upwards. So B2 is going upwards. So in this case, they are moving in opposite direction. So you have to assign also. So let's assign going out as positive. So resultant field will be B2 minus B1. Okay? Yeah. Clear. Okay. So that's why if you use the same method to look for the magnetic field at these three regions, so you will discover that the magnetic field on the side A and B will be higher because they are both B2 plus B1. It's the summation of B2 plus B1, whereas at P here, magnetic field is the lowest. Why? Because it is the minus, okay? B2 minus B1 is the difference between B2 and B1. So this one, when we change the directions of the wire. So check your answer on the pre-lecture video. Yeah? Okay, so now let's work on the example. We have two non-parallel wires, so carry current of 20 and 5 ampere. So let's assign it as I1 and I2. So the separation, meaning that, so if you draw them in diagram opposite direction, so one up, one down. So let's say this is I1, I2, and the distance between them is 0.2 meter. So find the magnetic field midway, meaning that at the center. Okay, so let's say this is point X. Okay, so using the same method to look for B1 and B2. Okay, B1 magnetic field generated by I1, B2 magnetic field generated by I2. Okay, so using right hand grip rule also. So right hand grip rule, stick your thumb on I1 going out. So at the center here, magnetic field is just going into. So B1 going into is a cross product. Okay? Now on I2, magnetic field, a current going downwards, so stick your thumb at I2. So when it passes through the center, it is also going into, so B2 is also cross product. So assign cross product as positive. So resultant will be B1 plus B2. Right? So resultant B so mu naught I1 2 pi R1. This is straight wire, so we use formula for straight wire. Okay. I1 is 20. So the distance between your wire and the midpoint, both wires are separated by 0.2, so at the midpoint is 0.1. Now move on to question B. At what point between the wire are the resultant field is 0? So meaning that resultant field equals to 0. So in order to get resultant field equals to 0, your B1 and B2 must be in opposite direction, right? Then you will get a chance to get VR equals to 0. If B1 plus B2, you will never get 0. So in order for you to get BR equals to 0, remember it must be B1 minus B2 or B2 minus B1. Okay, so where is the region whereby you will have both of them at different opposite direction? Then you check region by region. So there are three regions, A, B, and C, right? So we have already checked region B, it is B1 plus B2. So meaning that at this region, you will never get BR equals to 0. So either A or C. Okay, let's check at A, at region A, B1 is coming out from the screen. B2, thumb goes down, is going into the screen. At region C, B1 is into the screen. B2 is coming out from the screen. So it is either at region A or region C where you will get BR equals to 0. Okay? So let's say we assume somewhere here it is somewhere at region C. Just assume at the point. So we assume that this is the point whereby BR is equals to 0. Okay, so write your equation. BR equals to let's say it's B1 minus B2 equals to 0. So simplify, B1 just equals to B2. Okay, so B1 now is mu naught 4 pi times 10 to the power of negative 7, 20, 2 pi. So out here will be the distance between I1 and Y. So it is 0.2 plus Y equals to 4 pi times 10 to the power of negative 7, 5, 2 pi. So R2 is the distance between I2 and Y, so it is Y. Okay, solve to find your values of Y. Okay. So your Y is 0.07, meaning that it is 0.07 to the right of your I2. Okay? So I give you 5 minutes to digest first. Magnetic field, then we will move on to magnetic force. 5 minutes, come back at 9:24. difficult because it needs 3D imagination. But you digest first lah. You have to imagine in 3D because this one really involves in 3 dimensions. Okay, but you have to, or to make your life easier, or to make you can write your answer accurately. So we just use the dot and cross product to help you. But you have to imagine in 3D, so it's easier to know whether it's coming out or in. Okay, right? If I move to stage, what happened to your screen there? Oh. Oh, because this is my share screen. No. But just now before I move to stage, you'll see the small column only, is it? Y'all can make it maximum.
But they have the option to.
Maximum to change. Oh, okay. It's actually quite clear, kan, to see, but not as clear as the slide. Okay, so let's move on to magnetic force. So these are the prerequisites for magnetic force. Okay, in order for a wire or a charge to experience force, these three conditions must meet. Okay, first one, it must be a moving charge. So moving charge means a charge with velocity or current. Remember, current is a flow rate of the charge, right? Charge over T. I equals to Q over T. Means a moving charge or a moving charge also. It is actually a moving positive charge. The second one, so where does the charge move? The charge must move within a region with magnetic field. And the third one, the directions of movement must not be parallel to the magnetic field, meaning that there is an angle, so the angle must not be equals to 0. So these are the three prerequisites or the three requirements that must be met in order for a charge or a current carrying wire to experience magnetic force. Okay, so remember the directions of force must always be perpendicular to the directions of current and magnetic field, meaning that force must be perpendicular to current and force must be perpendicular to magnetic field. So how do we determine magnetic field? Using Fleming's left hand rule. So Fleming's left hand rule, now your left hand. So stretch your thumb, pointing and middle finger. Stretch them until make sure they are perpendicular. So thumb is perpendicular with your pointing finger, and thumb and your middle finger must be perpendicular also. You have to stretch until like this. I have students like when she says she is using Fleming's left hand rule, but then the directions always very odd one. So I asked her to show me. Then this is how she showed me. Because girls are very lazy, so cannot stretch. So she put like this. Cannot for this topic. You have to stretch as right as possible. Means 90 degrees. Thumb pointing 90 degrees. Thumb and middle must also 90 degrees. So if you feel how cannot like your hand is so very painful, then you have to train every day. Every morning when you wake up, stretch your finger. Make sure they are 90 degrees. Okay, so this is Fleming's left hand rule with thumb as the force, pointing as the magnetic field, and middle as current. So how do I remember FBI? Did you watch the CSI or X-File? FBI. Okay, F force, B magnetic field, I is current. Okay, so this one is for current carrying wire. Alright, so now let's look at this diagram. Here, let's try to determine the directions. Current going downwards, so middle finger going downwards. Now fix your current down like this. Then turn your hand. Magnetic field going into the page. Sorry, current is going upwards. In the diagram, current is going upward. So pointing finger going up like this. Now turn your hand until your middle finger going up. So turn your hand until your pointing finger points towards the screen. So where does your thumb show? It's just to the left. So make sure if your hand stretch like this, definitely 100% I guarantee you can get the correct direction. So that is where you find the directions. And to find the magnitude for wire, ILB. I is current, L is the length of the wire that covered by this magnetic field, and B is your magnetic field sine theta. Theta is the angle between the current and magnetic field. Okay? So in this case, your current is here, magnetic field is into the page. So in this case, your theta is equals to 90. So any angle can be your magnetic field and current. It can be any angle as long as they are not equal to 0. So meaning that just now when I said your thumb and your pointing finger must be 90 degrees, your thumb and your middle finger must be 90 degrees. But the directions, the angle between your pointing and your middle finger can be any angle except 0. Okay? Now, the self-exercises also you can double check your answer on pre-lecture video. So now I will only go through 2 and 3 with you. Again, let's try with your Fleming's left hand rules. Okay, current downwards, current down, so this middle finger going down, then fix here, turn your hand so that your B meet the diagram which is going into the screen. So where does your thumb shows now? To the right. Now, how about question 3? Again, I downwards, B coming out from the screen, so turn your hand, where does your thumb shows? To the left. Okay, so this one you can play around. So let's go through this question. The length of the wire is 120, force 1.8 when it is being placed in the uniform magnetic field of 2.1. So what is the current? This is a straight wire, so magnetic force by wire carrying current ILB sine theta. So maximum, meaning that theta equals to 90, sine 90 is equals to 1. Okay, so force 1.8, I unknown, 120 convert to SI unit. 0.71 ampere. Okay. So just now our prerequisite current, magnetic field, and theta not equals to 1. So just now we have ILB sine theta, right? So another one is when we have a moving charge, QV. So what if we have a moving charge? So instead of ILV, what we have here is QVB sine theta. Q is the charge in coulomb. V is now the velocity. How fast is the movement of the charge? Times with the velocity. And now the angle is the angle between velocity and magnetic field. So how do we determine the directions? We can also use in Fleming's left-hand rules. But remember, for Fleming left-hand rule is always FBI, right? So we have F still remain as the thumb, B still remain as pointing finger, but I here, it's only referring to the positive charge. Okay, so meaning that I will refer to the directions of the positive charge only. So in this case, let's look at here. Okay, magnetic field into the screen. So pointing finger point into the screen. Then velocity of positive charge is moving to the right. So where does the thumb show? Force is going up. Okay, positive charge. So let's go through question 3. Now, B is coming out from the screen, so pointing finger out, middle finger to the left, thumb going upwards, so force is upwards, so because this is positive charge. Now, how about if it is a negative charge? So negative charge, remember, if it is negative charge, meaning that it is actually the other way around, right? So this one is, remember, it must always be the directions of positive charge. So if it is, let's say question 2, if now this is a negative charge, it's moving to the left, so where does the positive charge go? Positive charge go in the opposite direction. So this is the directions of current, am I right? So if you want to use Fleming's left-hand rules, you have to first determine the directions of current, which is now going to the right. So with your Fleming's left-hand rules, B is into the screen. Your I is to the right. Where does your thumb show? Is going upwards. Okay, so that is the first method with Fleming's left-hand rules. But first, what you have to do, determine the directions of current. Or second method, instead of using left hand, you can straight away just use right hand for negative charge. So let's try with right hand for question 2. B going into the screen. Directions of the movement is to the left. So where does your thumb show? A is going upwards as well. Okay, so instead of left hand, use right hand. Okay, so both hand again is your best friend. So can I ask you all to try this? Remember to use the, okay, no dot and cross product, but you have to know the yellow color is the current and the charge. Oh yeah, this is the charge, so it's already shown positive and negative charge. So try to use Fleming left hand, right hand to determine the directions of the force. Brandon, you all can type your answer on the chat. Left, right, up, down. It's either left, right, up, or down, no? No, or dot and cross product. Left, right, up, down, dot, or cross. Okay. Okay. So let's get the answer together. Okay. So question 1. This is a negative charge. For negative charge, use right hand. B, into the screen. Stretch your middle finger. V, downwards. So where does your thumb show? Thumb is to the left. Am I right? Is it? Your Fleming's left hand rules. Huh? So it's to the left. That is your force. Okay? Can get that? Cannot. You have to stick on the screen, just point into the screen. B, just follow according to the orientation of this screen. So B is into the screen. So now this is my screen, no? So you can put your screen together here. So B is into the screen. Then the velocity is down. So follow the screen, it's down. So where does your thumb show? Isn't it to the left? So let's say if now this is how you put your screen, like here, okay? So I'm pointing into the screen towards you. So B is into the screen. Now velocity is down, right? So where does your thumb show? Isn't it to the left? Right. So yeah, your thumb is to the. Now this is the electron. So electron is using right hand, right? Okay, electron use right hand. If you want to use left hand, make sure it is. You find where the current goes. Okay. So now second question. Positive charge use left hand. So B is coming out from the screen. So pointing finger up from your screen. Velocity to the right. So where does your thumb show? Going down, right? Is it? Oh, thumb is going downwards. So force is going downwards. Now, question 3, positive charge again, so use left hand. Given that velocity is dot product, means velocity is coming out from the screen. So your velocity coming out from the screen, but your B is to the left. So turn your hand to the left. Right. So where does your thumb shows now? Isn't it going up? Question 4. Velocity is now going upwards, so middle finger point up. B to the right. So to the right. So where does your thumb show? Is into the screen now. So it's a cross product. Alright? So you can go through more self-exercises on pre-lecture video. Remember to go through these 2 topics, especially the next topic also. It's okay to make mistakes now rather than during exam. So hopefully this one can help you to get a clearer practical experience or exercises on using that means left hand user. Okay. So for moving charge, if it continue to move in the region with magnetic field, what will happen is it will eventually form a circular coil. So if this is the directions of your initial movement, then this charge will eventually form a circular pathway like this in clockwise directions. So in your, what you have learned in circular motion in first semester, when anything moving in a circular pathway, it is also tied to a centripetal force. Am I right? So this centripetal force is equals to mv squared over r. So in this case, the charge is moving in a circular pathway is due to the magnetic force as well. So we will equivalent magnetic force equals to centripetal force. So magnetic force QVV equals to NV over R. With this V is the velocity of the charge, and R is the radius of circular pathway. Okay. So now let's look at this exercise. So radius 3.8 centimeter, magnetic field strength 1.2 Tesla. So find velocity. So it's already moving in the circular pathway. So magnetic force equals to centripetal force. So proton, charge of proton 1.6 times 10 to the power of negative 19. Velocity unknown, b 1.2. So mass of proton 1.67 times 10 to the power of negative 27. Velocity unknown. Radius 0.038. So simplify. So that is your velocity, all right? Okay, so the force between two parallel wire, I will cover it during tutorial workshop time. Okay, so what I need you to do now is to get yourself familiarized with how to find the direction. So these two topics are it's been recognized as the hardest topic in semester 2. So I will need you to get yourself prepared, especially for the next topic. You must master this topic in order to proceed to the next topic. Okay, so if you find today very difficult to determine the directions, I think the calculation wise will still be okay, just the directions. So if you find you have difficulties, then I will need you to spend more time to try on the exercises. What you say? Not yet die lah. Okay, try on the exercises. Okay, especially in get used of like how should you orientate or how should you place your hand. Okay, because you will all need this in the upcoming topic. Okay, so please master this one and make sure watch the 3 lecture videos. So all this will be explained in the whole lecture videos also. Okay, so I will see you tomorrow for tutorial workshop. Not die, whatever that cannot, whatever that cannot kill you will make you stronger. So this is only foundation. Don't die. Okay, so I will see you tomorrow. If you have any question, just do not hesitate to message me. Okay, but please make sure you master all these before tomorrow, so that you will feel much happier tomorrow. Okay, so I will see you tomorrow. Bye bye. Thank you.